All right, welcome everyone to our second to last Origin seminar of the semester. As a reminder, please turn off your video unless you're speaking to conserve bandwidth, and try to hold your questions until the end of the talk. If you have a clarification question that just cannot wait, you can type that into the chat and then I will ask it to the speaker. So today's speaker is Sebastiaan Haffert. He got his PhD from Leiden Observatory and is currently a Hubble Fellowship Program Sagan Fellow here at Stewart Observatory, where he is a member of the MAG-AOX team and, of course, one of the organizers of this seminar. And today he's going to tell us about his work with high contrast imaging. So take it away, Sebastiaan.
Yes, thank you for the introduction. So today I'm going to give a bit of an overview of the work that I've been doing with high contrast imaging in young stellar systems. So it's going to be a bit of a wild ride, but hopefully everybody can hang on. So this is a typical schematic of what we think how planet and star formation and how planetary systems, how they form. So everything, of course, starts a giant cloud of gas and dust, and that all collapses. And then during that collapse, a lot of interesting things happen. But I would like to focus on this stage, on the stage where we still have a protoplanetary disk or circum-stellar disk around the star. So nowadays, there have been many observations with ALMA, so in sub-millimeter of these disks. We see a lot of interesting features. We see rings, gaps, spirals, and we really want to understand how they all came to be. Because one of the most used answer for these features is that there are planets in these systems that are creating these features, and we really want to find them. So this is the sort of structure that you find with ALMA. But if you go to the near-infrared, you also get a lot of structure in the circumstellar disks, and it's also a little bit more chaotic if you compare the two. So here you can see several images from different systems from the DART survey, which was done with sphere at the VLT. But this is in the near-infrared. We can even go one step further in the blue, and we can go to the visible. However, there's quite a challenge in the visible with direct imaging. So with direct imaging up to now, we've mainly done that in the near-infrared, and we can actually find exoplanets, and we can also, of course, as I shown before in the last slide, you can search for disks, and it works quite well in the near-infrared and at longer wavelengths. However, when you go to the visible, so here you can see sort of the performance difference that you can get between the near-infrared and the visible. So on the left, we have an H-band PSF from Sphere, while on the right, we have a R-band PSF from MAG-AO. So while I'm saying that this is a PSF for MAG-AO, the PSF for Sphere in the visible or any other high contrast imaging system in the visible, they all are roughly equal performance. So it's all relatively low strail. And that means if you look at a standard high contrast imaging system, that sort of looks like this. So you start with your telescope on the left, that goes through an adaptive optics system to clear up turbulence in the atmosphere. And then you go through a coronagraph to block out the starlight. And then after the coronagraph, you have your science instrument. However, for the visible, because the AO performance is not very high, coronagraphs are not really used because they do not contribute. They cannot do anything because of the low performance. So in the visible, you have this situation where your science observations and your data processing has to do a lot more work relative to the near-infrared. So if you want to do high contrast imaging in the visible, you need to do a very good post-processing. So I do that a lot with integral field spectroscopy. So here you can see a schematic of an integral field spectrograph. So the data that you get out, of course, is just a spectrum for every pixel in the field of view. But there is a difference in post-processing whether or not you do this at low spectral resolution or high spectral resolution. So if you have a low spectral resolution integral field spectrograph, then your PSF, you see significant change in the PSF between different spectral channels. So here you can see 3 PSFs taken that are far away from each other in wavelength space. So then if there's one spectral channel, like the middle one, that has a star plus planet signal, and the other two don't have any planet signal, that means you can use those channels at the edges to model the PSF and subtract your star. However, as you can see here, if there's a large difference in wavelength, the PSF don't look alike. So the PSF changes with wavelength. However, if you go to higher spectral resolution, and your channels are very close together, then it's much easier to model the PSF because the PSFs of the other adjacent channels look very similar. So with high resolution spectroscopy, you can very accurately model the PSF and subtract it out. Which is also why I think that high resolution spectroscopy is really convenient to use in the visible, because we need to do post-processing very well, because we cannot do chronography. So most of my observations up to now have been done with MUSE spectrograph. So here on the right, you can see an image of MUSE at the VLT. So here is MUSE. MUSE is quite a large integral field unit. So it has 24 detectors and 24 spectrographs. And they are fed by a laser tomography AO system that you can see here on the right. So you can see the sodium guide star lasers of the LTAO system. So on the left, you can see a couple typical parameters of MUSE. So typically the spatial resolution is about 50 milliarc seconds. And that's sampled by pixels of 25 milliarc seconds in size. And the resolving power is roughly like 2,000 to 3,000-ish over the spectral range. And MUSE has a relatively large field of view, or at least this is the parameters that I show here are for the narrow field mode. So that's the high spatial resolution mode. And it has a 7.5 arc second field of view. The laser tomography, the LTAO system itself, it delivers typically a strail between 5 and 20%. Depends very strongly on the seeing and the atmospheric parameters, because in the visible, you are very sensitive to the atmospheric conditions. And you can use targets that have an H-band magnitudes up to 14 for this system. So there's a really large range of objects that you can look at with MUSE. So with MUSE, I've done a lot of characterization of young exoplanets and their environment. So one of the most famous examples, I think, is PDS-70. So PDS-70 is a young T-Tauri star. There's a circum-stellar disk with a large gap. And in that gap, there's been, we have found 2 planets. So the first planet has been found by near-infrared imaging. And the second planet has been found later by H-alpha imaging with MUSE. And the reason why that's very efficient is because when the planets are in the gap, there can be still some gas and dust in the gap. Well, mainly that gas will be accreted by the planets. And when it arrives at the surface of the planet, or it arrives on the circumplanetary disk, it gets shocked. And that shock can create a lot of H-alpha emission. And that H-alpha emission makes it, at least the contrast decreases significantly between the planet and the star. So the H-alpha peak emission can be much higher than the photospheric emission from the planet itself. So H-alpha emission is in principle a very good way to detect these planets. So we were also successful with MUSE. So here you can see on the left our first image of the detection. So here we have the B companion and the C companion together with the spectra. And after we found these planets, we wanted to do more observations. because PSFT is an interesting case study. It's currently the only known system with confirmed accreting protoplanets. So to accurately characterize these systems, we applied for observing time on the VLT, and we got, in the end, we got about 10 epochs that sparsely sampled the period from April 2019 to August 2019, with a total integration time of about 16 hours. So this is about a factor of 30 increase from our first detection. So in signal to noise wise, we expect an increase in factor 5 to 6. So we can probe significantly deeper for features. So the first thing that you can do is, if you have a time series, is to search for a variability in the H-alpha emission. So here you can see the images for every epoch. And the planets are detected in almost all epochs, or at least they're detected in all epochs. And sometimes the only thing that's difficult with these observations is that it's sometimes a bit more difficult to filter out cosmic rays. So for example, here you can see in one of the epochs, there are 2 cosmic rays that are corrupting the image a little bit. So the reason why the cosmic rays here are still present is because this was a very short observing sequence. We only got 3 exposures of 100 seconds each. And because of that, it was difficult to filter them out. But even with only 300 seconds, we were able to detect both companions. And that was because we had very good atmospheric conditions. So we had a seeing of 0.25 arc seconds during these observations. So with only a single exposure, we could already detect both companions. And this shows really that MUSE, or at least high resolution spectroscopy for H-alpha emission, is really, really efficient. So if we look at the normalized flux itself, it's quite, it changes all over the place. And this is even after we have corrected for the stellar PSF and for the seeing and for the atmospheric transmission. So here you can see in blue the H-alpha variability of PDS70B, and in orange it's the H-alpha emission for PDS70C. In green, you can see the flux that we get from injected fake planets. So we inject fake planets into the data set to calibrate both the post-processing algorithm and the effects of that the PSF have on the loss of flux. Because due to the strong seeing conditions, it could be that a lot of flux is lost outside of your photometric aperture. And to calibrate that, we use these fake injected planets. So even after calibrating with these fake injected planets and all the other steps, we can see there's still a lot of systematics. And the reason why we think it's systematics is because both B and C have the same sort of trend and the same behavior between them. So what I then looked at was the ratio in H-alpha flux between B and C. So that's what you can see here on the right. And as you can see, most of the most of the points are actually very close to the initial flux ratio that we measured of about 0.5, 0.6. There's only 2 points that really deviate from this initial measurement. And if we look back at the epoch, at those 2 epochs, we can see that in the first point that's deviating, we see that the strail, or at least the quality, is really poor. So we have really low signal to noise data, and there's a lot of residuals. And in the second, so the second point, we see the same thing happening, is that there's a very strong residual structure around the B companion. So I think these 2 points that are deviating is most likely instrumental. So in conclusion, what we then can say about variability is that the 2 planets are probably not variable, or at least not within about roughly like 20%. So we have a 20-30% error margin on the variability. And within that error margin, we don't see the companions vary. So of course, because we're now looking at the flux ratio between B and C, it could be that both companions are variable at exactly the same rate and with changing exactly in the same way. That's something that we cannot see, and I find that quite unlikely. So the most obvious answer is that the two companions are not variable, or at least not strongly variable on the time scale of a year. So we can also look for, instead of variability, we can add all the data together to search for other companions. So that's what you see here. So on the right is the original detection image, and on the left is the detection after stacking all the data. So our signal to noise became much better. We have sadly found no other planets. So there has been evidence by sphere images, by sphere observations, that there could have been a second companion or a third companion closer in, but we have not found that companion. So it was most likely a instrumental artifact, that third companion. So we can also see a large quality improvement in the extracted spectra. So on the right, you see the original spectrum of B and C. And here in the middle, you can see the extracted spectra of the star, the B companion, and the C companion. And you can see already in the quality of the spectrum that we really increased our signal to noise. So based on the spectra, we can see that the signal to noise increased by almost a factor 4. And this is very close to the expected increase of a factor 5 to 6, based on just the exposure time. The reason why you have not reached that factor of 5 to 6 is because the seeing and the atmospheric conditions also play a strong role in the actual signal to noise that we achieve. And that's not factored in this number. But I think what this already shows is that we can, with this type of observing techniques and with MUSE, we can actually do very long integrations, and we can stack the data and see an increase in signal to noise, even beyond single nights. We can even stack multiple independent nights to increase the signal to noise. So instead of H-alpha, we can also look at other emission lines. For example, a very important one is H-beta, because if you detect H-alpha and H-beta, you can actually constrain the accretion rates and the and maybe the extinction. However, we have detected no H-beta from both companions, and we have derived an upper limit of a 1:5 ratio. So this is a significant increase. With the original data, we could put a constraint of about 1:2 or 1:1. And as you can see, we are now a factor 4 better. And we can put an upper limit of 1:5 of the H-alpha to H-beta ratio. So can we learn something from the system? Probably not is actually is the answer. So here I'm plotting the results, plotting the H-beta over H-alpha line ratio for a planet accretion model that was created by Aoyama and Ikoma. And this accretion model is a function of the free fall or of the infall velocity of the gas on top of the planet, and the column density, the density of the material. And in white and cyan, I've drawn the contour of the 1:5 ratio for 3 different cases. So on the left is the case if there was no extinction to the planet. In the middle is the most likely extinction based on the work from G. Wang et al. And on the right is the case for strong extinction that was also based on the work by G. Wang. So they have observed the PSFT system with gravity, the interferometer at the VLT. And with that, they were able to get K-band spectra of both companions. And together with the other L-band photometry and the Y to H-band spectroscopy, they were able to get a sort of a grip on the extinction. But that extinction currently says that the most likely extinction is probably 2 or 3 magnitudes, but then with an error bar of about 3 magnitudes. So within the 1 sigma error bar, you can go all the way from practically no extinction for the current best fitting models to a strong extinction of almost 7 magnitudes for the B companion. So given that the extinction is very unknown, we cannot actually put constraints on the accretion, or at least on the parameters of the accretion. So that's a little bit too bad. So if we compare this with other emission lines, other upper limits, so recently there's been a paper that has been, or at least a research note that has been published where they show the upper limits for the Paschen beta line. And in the same graph, they have the density versus velocity again, but this time for the Paschen beta over the H alpha line ratio. And they reached sort of a similar conclusion. So both graphs here are shown for no extinction. And what it shows is that there is a preference for low velocity solutions, which means a low mass planet, because only low mass planets have low infall velocities. However, this is all under the assumption of no extinction. And I don't think that is actually true for these systems.
Sebastian, before you move on, we have actually a couple of questions. One from Andrew Uden, which I believe was on the previous slide, asking why the units of column density are squared and not cubed.
Yeah, so that's because it's the actual density.
Cubed and not squared.
Density.
Right.
So it's the label is wrong, not the units. I'm sorry.
Right.
It's the actual hydrogen density.
And then we have a question from Everett who asks what the contours are.
Oh yeah, so these contours are the line ratios, or the measured line ratios.
All right.
Yeah, so the graph is the colors. The color map shows the model line ratios, and the contours are the measured line ratios. It's the measured line ratio. And this is an upper limit. So that means that everything darker than this upper limit is likely, or is possible. But this is only for the unextincted case. You can also look at it in a different way, where instead of looking at it in a 2D map, we can plot it as function of the H alpha flux. And then you can plot the flux of the line relative to H alpha. So what we detected in H beta is roughly, this is the upper limit, and this is the upper limit for the Paschen beta line. And you can do the same thing for the bracket gamma line that has been, for which we have an upper limit. However, the extinction makes it very difficult because the lines sort of give a rough estimate of how much extinction we can expect, or at least. So from this, what we see is that even though we have upper limits on a lot of these other emission lines, we cannot really learn anything from it because it's too much degenerate with the actual extinction towards the planets. We can also, of course, look at other emission lines and see what we can learn from that. So here I'm showing the detection maps of H beta, oxygen 1, H alpha, S2, the calcium IR triplet. So not all, yeah. So on the top you see the detection map, and on the bottom it's the same map, but then I've increased or decreased the color map scale, so that's more, so that faint structure is more clear. And in all the lines, I've injected companions to the level where they are still sort of visible by eye. So that's a rough upper limit that will give us a rough upper limit on the detection. So as you can see, we have detected no H beta, no oxygen, no S2, no calcium IR. So at the moment, the only emission line that we have detected is H alpha. So if we compare this to other brown dwarfs or other low mass companions that are accreting, we can see that the line ratios of PSFT-B they are quite comparable, or at least comparable to at least the upper limits. They are not weird. So we have observed 3 brown dwarfs with MUSE, or at least these 3 are derived from our MUSE observations. And we can see that the H alpha and or at least the H beta to H alpha line ratio is typically like 1:7 or 1:6. And for 2 other targets that have been observed by other people, they are that ratio is even lower. It's 1:9 or an upper limit of 1:10. So the fact that we've detected we have an upper limit of 1:5 is not really something that's worrisome if we compare to other objects. But it's a little bit too bad, because without that detection, we cannot put any constraints in. So for the other lines, we see, again, comparable numbers that are in the range of what we have found for other objects. However, because there's only been so few objects that have been characterized in detail, or at least their accretion hasn't been characterized so much in detail, we cannot really draw any conclusions yet on the other emission lines. Currently, there's only been modeling done for the hydrogen lines for accreting planets. So we don't even have models yet that can relate the accretion or can use these line ratios to constrain the accretion rates. So in conclusion for PDS-70 is that we have detected no new companions. We have detected no new emission lines. There's no apparent variability on the timescale of a year. And we have reached the effective noise limit of MUSE because we have used 16 hours of observing time. And the only way we can actually deeper is if we can do something on the order of 100 hours, but that's maybe tricky to get. And I think a real conclusion that we can take is that it's really difficult to constrain the mass accretion, or at least constrain the parameters without a better constraint on the extinction. So I think the future characterization efforts of PDS-70 should really be focused on getting a better handle on this extinction. So if we go to heavier objects that are slightly easier to characterize, you can actually do broadband characterization in the visible. And that's also important. So here you see an image of the CSCHA system, where in the middle you see CSCHA, and then here's the companion CSCHA-B. And CSCHA-B was quite peculiar because it was very strongly polarized. With SPHERE, they've detected a 10% polarized signal, and it was quite weird. And it was thought to be a low mass companion based on IR broadband photometry. However, so we took a spectrum with MUSE, and we were quite successfully in getting the spectrum out. So here you can see in black the actual measured spectrum, and in blue the residuals due to the halo of CSCHA. And we can see here that there are 3 emission lines detected for this companion. So we have H alpha, the oxygen 1 line, and then the oxygen, and then another oxygen 1 line. But what's a bit weird about these lines is that the H alpha to oxygen ratio is quite large. So the oxygen emission is quite strong relative to the H alpha. And another thing that's a bit peculiar is that it's very faint. So it's very faint. The photospheric emission is also very faint. So if we combine that with the near-infrared photometry and fit the data, or fit models, we actually found that the best fitting model was a high temperature model. So instead of the proposed 1700 or 2500 Kelvin, we found almost 3500 Kelvin as the best fitting model. So that means that this object would be going towards temperatures of low mass stars. And that's also what we think is happening in this system. After fitting it with stellar templates, we found that the best fitting spectral type was an M4 spectral type. So that means that this would be an M dwarf. But how is that compatible with the low emission, the faint emission that we see, and with the emission lines? So what we think is that this is a disk obscured star. So you have the star in the middle. It has some accretion funnels, and it has an outflow, and there's a circumstellar disk. But that circumstellar disk is aligned with our eye. And because of that, we only see light that is scattered from the disk edge. So either it could be backward scattering from the backside, or it could be forward scattering from the front side of the disk. And that creates a very faint signal. So you get a signal that's comparable to like a planetary mass object, but it also is strongly polarized because you look at this single scattering event. And the second thing is because the disk, it blocks the accretion funnels and the accretion hotspots on the star. So that means you also block the light towards the H-alpha emission. However, the outflows, they are perpendicular to the disk. So those are less obscured by the circumstellar disk, and that creates a larger oxygen to H-alpha ratio. So what we think is that this object is actually a disk-obscured M dwarf. So it's not a planet at all. And adding the visible spectroscopy really helps because it can really bring down this degeneracy with the extinction. And it's not like CSCHA is not the only object where something like this is happening. So there's a couple other handful of targets that are mimicking planets, but are actually stars. So recently there was an object detected. So I think it was CRA9, if I remember right. And they've done near-infrared spectroscopy and K-band spectroscopy and all those observations, and they were not able, with only the near-infrared observations, they were not able to constrain whether or not it was a planetary object or it was a stellar object. So I think this really shows that adding visible light, or at least visible observation, is really necessary to help constrain the properties of the companions. So and again, just like PDS-70, in the PSFT system, in this system, the extinction again played a major role in the characterization of the companion. So these are the types of things that we can do for companions, but we can also look at stellar outflows. So stellar outflows in the visible also contain a lot of emission lines. So one of the objects that we looked at is HD 163296. So last week we had a very nice talk about this object from the perspective of the MAP survey. And here we are showing the MUSE observations. So one thing that we see is that it's quite asymmetric. So we have the jet on the front side and the jet on the back side. You can see that the front side is almost like a continuous stream, while the back side shows just a single blob or a knot. If we look at the mass loss rates from these jets, then we see it's quite small. It's about 10 to the minus 10 solar masses per year. So per structure, so this side and both sides have a 10 to the minus 10 or 5 times 10 to the minus 10 solar mass per year mass loss rate. This is, if we compare it to the mass accretion rate, it's about 6 to 8%. And this is consistent with earlier observations that looked at larger scales. So in Ellerbrook, So in Ellerbrook et al. In 2014, they've shown the outflow. So here you can see the jet in H-alpha. So on the x-axis, or at least on the horizontal axis, we have the distance from the source. And on the y-axis, you see the velocity. And you can see here these jets coming out. So the mass, or at least the relative mass loss rate compared to the mass accretion rate that they measured is quite similar to what we measure. So we see a very constant mass loss rate as function of distance. And it means that it's also quite constant as function of time, because these ejection events, they occur at a different time, because as time goes on, they move away from the source. So if you invert time, a larger distance means longer ago since the mass was ejected. And if that is consistent through time, that means that the accretion rate and the ejection rates are also relatively constant. So one thing that you can see here is that it seems to be that the nodes are ejected quite regularly if you propagate them back. And it seems that the period is about 16 years. So every 16 years, we see a node that's ejected by this system. However, this new blob that we detected, or this new node, if we measure its velocity and its distance from the star and take into account the inclination, the ejection time actually does not match that 16-year period. So that means that either that 16-year period is wrong and there's a different ejection period, or as another likelihood, or the thing that's likely, is that this new node is still part of the previous node. And the third one is that this node is actually not a node, but a completely just a jet that's similar to the other side. However, it's extincted by the gas disk surrounding HD 163296. And from what we saw in the results from the MAPS imaging from last week of the gas disk, the gas disk of HD 163296 is actually quite large. So it's very likely that this jet is actually obscured by the gas disk. So instead of being a node and being an independent structure, it's actually just a continuous jet that is being extincted. Another thing that we could do is we could trace the size of this jet, of the front jet, as functional distance from the source. And we can fit how this width increases. So we're measuring the opening angle of the jet. And we can also measure where the jet starts. And from this, we find that there's a launching radius of about 1 AU, plus minus 1.3. So within the arrow bars, it's pretty much launching from within the innermost region of the system. So this is really consistent with just an ejection from the stellar surface, or at least its near vicinity. So we can characterize the stellar jet down to several tens of AU. We have detected a new node, and we see that it has a different period, or it could be extincted by circum-stellar disk, and we have constrained the jet launch radius. And recently, we've detected a new outflow. So this is the outflow in the CT-CHA system. So CT-CHA is a classical T-Tauri star. It's about 0.9 solar masses. And it also has a low mass companion, CT-CHA-b, which I've indicated its rough position with the yellow star. And that's a 10 to 20 Jupiter mass companion. So there has been evidence already for the outflow in earlier X-shooter spectra of CT-CHA-a, where they've detected oxygen emission. But the outflow itself has never been detected. So if we compare, we can compare the two outflows detected with MUSE. So on the left, we have CT-CHA-a, and on the right, we have HD 163296, and we see that they're quite different. So the outflow here has a much larger opening angle than the outflow in the HD 1636 system. And also, if we compare or try to estimate the density, the electron density of the flows, the density on the for the object on the right is much higher than the density for CT-CHA. And this difference can, of course, be caused by the difference in mass. So CT-CHA-a is a T-Tauri star, while HD 163296 is a Herbig AB star. So that's a large difference. But that low density for CT-CHA is also the reason why it was difficult to detect before, because the emission is really faint. So you need to have a high performance, where you need to get good AO observations to actually see this. We can also look at it in different velocity channels, because MUSE is a spectrograph. And there we see quite interesting structure. So on the front side of the jet, we see that at high velocities, we see quite a collimated outflow, while if we go to lower velocities, the outflow becomes wider. And you can also see that here there seems to be a bow shock and a bubble being created. So probably the jet is colliding with circum-stellar material, which stops the jet. Now we have to. Then there's the backside of the jet, which is also has an interesting structure, because we have the outflow near the star again, which is bright, but then far away at 200 kilometers per second, there's another bright knot within the jet. I'm not quite sure what is causing that. So of course, you can look at different emission lines. So you can look at the oxygen lines, again, the H-alpha line, the neon line, the S2 lines. So here you can see in the H-alpha, you can clearly see the brown dwarf companion that is accreting. So we have detected multiple emission lines. And one thing that we can do, just like with the HT 163296 data, we can again trace the full width maximum of the jet as function of distance and see what the opening angle is and try to trace it back. However, because for this system, we can actually resolve the different velocity channels quite well. So we can trace this evolution as function of velocity. And we think that that is important to do because you can see that the morphology between the different velocity channels is quite different. So here you can see the full width maximum as function of distance for the three velocity channels. So minus 50 to 50, so that's the stellar rest frame, minus 50 to minus 150, and then minus 150 to minus 250 kilometers per second. And what we see is that at all distances, the full width maximum is decreasing with velocity. And for the oxygen line, we see that the high velocity channel seems to have an intercept close to zero, while the low velocity component, the green one, is intercepting at a different full width maximum. So it could be that there is a difference in ejection radius at the different velocities. And that may be one of the things that could cause this is a disk wind. So if you have a disk wind, you also eject material with different radii compared to the jet. So this is still ongoing work to improve the results a little bit to see if we can get a better constraint on that intercept, because I think that is very interesting. So in our CT-CHA summary, we have detected the new low density stellar outflow. It has a very wide opening angle, so it's about 45 degrees. And the launching radius seems to be depending on the velocity in this system. So now we've gone through the presentation. I've shown you a little bit of what we can do with visible light, high contrast imaging. And I think it's a powerful technique to probe the young stellar environment, because we can do detailed characterization of young objects. However, it is really limited by our knowledge of the extinction towards the object. And on the other thing is we can find very faint emission lines and probe very close to the star, both for extended and point source emission. Yes, so thank you. And people can ask questions if they want.
All right, thank you, Sebastian. If you have a question, you can either type it in the chat or you can use the raise hand feature. And I see that we have a question from Ilaria, who asks, what is the estimated opening angle of the jet from HT 163296 and for the jet and wind from CT-CHA?
Yeah, so for CT-CHA, it's about 45 to 50 degrees. So it's quite wide. While for HT 163296, it's more between like 5 to 10 degrees. So it's a significant difference in the opening angle.
All right. And then we have a question from Laird.
Yeah, Hey, thanks for the talk, Sebastian. That was great. Very interesting. And of course, you're quite right. The extinction is a little tricky for the H alpha because, of course, there is significant extinction out there. But one of the things that I mean, I know you know about, but it's worth mentioning is that PDS70B has actually been imaged with MAG-AO, and it's also been imaged with HST now. And the HST work was kind of great because they could go really far into the blue, all the way out to the bomber jump at 363 nanometers, and there was actually a pretty substantial excess detected in the UV from B, which is great, not too surprising. But what it means, I believe that work also it was hard to reconcile the with just a simple slab model of emission. It was hard to reconcile that UV emission with having a lot of extinction from B, because of course in the UV the extinction is so rapid. And anyways, long story short, I think they sort of came up with EFAN model. I mean, I guess it's part of the effort too. Came up with something around 3.5 magnitudes as kind of where it was getting pretty inconsistent with other observation. Now, of course, something that's stymieing us a little bit is that, of course, the accretion physics could be quite different on a planet compared to a low mass object. But nonetheless, if it's similar, then sort of extinctions around 3.5 magnitude seem to be about the maximum. So, I mean, it's just another, you mentioned yourself that it's sort of an upper limit of 3 magnitudes, but
Yeah, I think with such an extinction, so that's in between the most likely extinction and the strong extinction.
Yeah.
So it's really difficult to put some constraints on this.
Yeah, no, I know it's a little frustrating. But if it was also very high extinction too, you'd think that maybe the Passion beta would show something in the infrared.
So I mean, that's very difficult. I mean, they've already have a line ratio upper limit of almost 1:30. So that's pretty steep line ratio. But also, if you look at the actual flux, is that there are a lot of situations where the actual line ratio can actually be 1:100, depending on the actual physical conditions.
Yeah, that's tough. Yeah, that's tough. 1:100 is pretty tough.
Yeah. And Passion beta is better than bracket gamma. So for bracket gamma, the line ratio decreases by another factor of 10.
No, Passion, bracket gamma is fairly useless.
So
H alpha wins. H alpha wins by a lot.
Yeah, in detection, but you cannot use it for
extinction.
Only using H alpha is difficult for characterization.
Right. Well, I don't know if we'll be able to detect many more UV emission systems with HST, but that's a possibility too. All right. Thanks.
All right. Any final questions for Sebastian? Everett.
Thanks for the talk, Sebastian. I was wondering if the line width tells you anything about the accretion, or is it just unresolved?
Yeah, so the line width in principle could tell us a lot about, I think the line width is mostly constraining the velocity of the infalling velocity. However, the intrinsic width of the lines themselves is about a resolving power of like 15,000. So you need to have a spectral resolution of 20 kilometers per second, on the order of that, to actually detect that. And MUSE has a velocity resolution of like 120 kilometers per second. So it's a factor 6 too low to actually detect this well.
Is that something that would need a new instrument then, or?
Yeah, I would say we need to have a higher resolution spectroscopy.
Thank you.
I think there's a question from Kevin.
Yeah.
Hey, nice talk, Sebastian. I'm kind of wondering where the fake planets are, or the planets that you injected in these different line images, so like the H beta and O1. Could you possibly point out where those are? And well, what I'm wondering about specifically is this source that looks like it's in the position of PDS70b for H beta and O1. So I'm wondering if you injected a fake planet where you expected to find the source in addition to what appears to be these wider separation ones.
Oh yeah, so for the emission lines where I have not detected the companions, so that means everything else in H alpha, I've also injected fake planets at the position of the two companions, just to get a feeling of what the sensitivity is at the exact position of the two companions. So it's not, this is not signal of PSFT plus the injected fake companion, it's only the fake companion.
Okay, thanks. Well, that's a bit less exciting than what I had hoped for by looking at the image, but that makes a lot of sense.
All right, additional questions? If not, thank you all for coming. We're off next week, but please come back in 2 weeks for our final talk of the semester. And at this point, I would like to encourage everyone to unmute and thank Sebastiaan for a great talk. Thank you, Sebastiaan.
Thank you.
Thank you.